Welcome to the Deep Dive. We're here to explore some really fascinating ideas and, give you a clear picture without making it too complicated.
That's the plan. We
Right.
know you like to learn quickly, get those aha moments.
Exactly. So you sent us these 7 short lessons on physics.
Yeah, and our mission today is to unpack them for you, especially if physics isn't really your main thing. We want to make it, well, maybe even exciting.
Sounds good. We'll take each lesson one by one, build things up.
Right, so we'll cover Einstein's big ideas, then quantum mechanics.
The universe itself, tiny particles.
Yeah, quantum gravity, black holes, heat.
And finally, where we fit in all this cosmic weirdness.
Exactly, step by step.
Okay, let's dive in. First lesson, the most beautiful of theories. This is about Einstein's general relativity, right?
It is. And it's funny, the source mentions Einstein spent a year just kind of loafing aimlessly in Italy when he was young.
Loafing doesn't sound very Einstein-like.
Well, maybe not the image we have. But it kind of shows that downtime, letting your mind wander, that can be really valuable for, creativity, for learning.
That's actually a relief to hear. It's not just about grinding away all the time.
Definitely not. So after that, he did get serious, studied physics hard in Zurich, and then bang, 1905, this incredible year.
Right, he published 3 huge papers.
3 huge papers. Any one of them could have won a Nobel. He wrote about atoms being real, the start of quantum mechanics, we'll get back to that, and special relativity.
Let's pause on special relativity. That's the one with the weird time stuff.
That's the one. The really counterintuitive idea that time, well, it doesn't pass the same for everyone.
How can we picture that, simply?
Imagine you have 2 perfect clocks. Send one on a super fast rocket, near light speed. When it comes back,
What happens?
it'll show less time has passed compared to the clock that stayed put.
Seriously. So time literally slowed down for the traveling clock.
Yeah. It's wild, but that's what happens. Time isn't this, universal constant tick-tock for everybody.
Mind blown already. Okay, so that was special relativity. But he didn't stop there.
Nope. He knew gravity didn't quite fit with special relativity, so he spent, the next 10 years wrestling with it. Just intense work.
10 years. Wow.
Yeah. And finally, November 1915, he cracked it. General relativity.
Yeah, and that one's seen as, a real masterpiece.
Oh, absolutely. The physicist Lev Landau called it the most beautiful of theories. It's up there with, Mozart's Requiem or the Odyssey. It just fundamentally changed how we see everything.
The source mentioned someone getting that aha moment on a beach, picturing space curving.
Yeah.
That's the feeling we're aiming for, right? That sudden clarity.
That's exactly it, that click. So before Einstein, Newton thought of gravity as this invisible force pulling things through empty space.
Right, like apples falling.
Yeah. But Einstein's idea was radically different. He said the gravitational field is space.
Wait, gravity isn't a force in space? It is space. How does that
Yeah.
work?
Okay, think of a rubber sheet, stretched tight, put a bowling ball on it.
Okay, it makes a dip.
Right, a curve. Now roll a little marble nearby. It doesn't go straight, does it?
No, it curves around the bowling ball.
Exactly. Not because the ball is pulling it with some magic force, but because the sheet itself is curved. The marble's just following the curve.
So the sun curves space, and Earth follows the curve, like the marble.
That's the core idea. The curve is what we experience as gravity.
That actually makes more sense. Less mysterious force, more geometry. How did he describe that curve with math, though?
Well, he built on work by earlier mathematicians like Gauss and Riemann. They'd already developed the mathematics of curved surfaces and spaces. Riemann had this thing called Riemann curvature. Basically, a way to measure how curved space is.
And Einstein saw that was the key.
He saw that was the key. He connected that mathematical curvature to gravity.
And it boils down to a simple idea.
At its heart, yes. The equation basically says the curvature of space, let's call it R, is directly related to the energy and matter in that space. Put simply, matter tells space how to curve.
Matter curves space. Wow.
And space tells matter how to move. It's this elegant dance. But from that simple idea, whoa, the predictions were wild.
Like science fiction, the source said.
Totally. Things that sounded crazy back then. Like it predicted light would bend around stars.
Oh, did it?
Yep. Measured during an eclipse in 1919, made Einstein famous overnight. It also predicted time runs faster higher up.
Faster, like on a mountain versus the beach.
Exactly. It's been measured. Tiny difference, but real. Your head ages faster than your feet, technically speaking.
Okay, that's bizarre. What about black holes?
That came from the theory, too. Regions where space is curved so extremely, matter just collapses inwards and nothing, not even light, can get out. Seemed impossible at first.
But now we think they're real.
Oh yeah, we see evidence for them everywhere now. And the theory also predicted the whole universe is expanding.
Which led to the Big Bang idea.
Exactly, that the universe started super hot and dense and has been expanding ever since. Discovered in the 1930s.
And we have proof for the Big Bang.
Strong proof, like the cosmic background radiation, the leftover heat from the Big Bang. It's a perfect match. And just recently, we've detected gravitational waves.
Ripples in space itself.
Ripples in space-time, predicted by Einstein over 100 years ago, now directly observed with incredible accuracy. Another massive win for the theory.
So this beautiful theory paints this picture of expanding universes, collapsing space, time slowing, space rippling. It sounds unreal.
It does sound like a dream, but it's the best description we have of gravity and the cosmos on a grand scale. It's a peek at a deeper reality.
And the equation itself, even if we don't, get the math.
Even if the symbols look like Greek, the underlying message is this beautiful simplicity. Matter curves space, space guides matter.
So lesson 1, general relativity, an elegant, game-changing view of gravity, space, and time. A new way to see the universe.
Couldn't say it better myself.
Yeah.
Sheer beauty and new eyes to see the world.
Okay, on to lesson 2, quanta. Now this feels like a totally different beast compared to smooth, curved space.
It really is. General relativity, it's this grand, coherent vision from one mind. Quantum mechanics. Well, it's been massively successful. It's the foundation of modern tech.
Computers, laser.
Right. But it's also deeply weird, still baffling even after a century.
So where did this weirdness begin?
It arguably started around 1900 with Max Planck. He was trying to figure out the light coming off hot objects, like a hot poker.
Okay.
And the only way he could get his math to match experiments was to pretend energy wasn't smooth and continuous. He had to imagine it came in little chunks, little packets. He called them quanta.
Like energy was lumpy, not smooth.
Exactly, like tiny marbles instead of flowing water. It completely went against what everyone thought.
Was it just a math trick for him?
Pretty much, at first. He wasn't even sure if these quantas were real. It just made the numbers work. But then, 5 years later, guess who pops up again?
Let me guess. Einstein.
Einstein. He took Planck's idea and ran with it. He showed that these packets of energy were real, at least for light. He said light itself is made of these particles.
Particles of light.
Yep, we call them photons now. Tiny bullets of light energy.
So Einstein made Planck's math trick into actual reality.
He did. Described light energy as being discontinuously distributed in space, these energy quanta. Hugely revolutionary. People were skeptical at first, of course.
But it won him a Nobel Prize eventually, right?
It did. So Planck planted the seed, but Einstein really nurtured it, showed these quanta were fundamental.
Okay, so we have quanta. Who took it further? Niels Bohr.
Niels Bohr, yeah. Danish physicist. In the 1920s and 30s, he was key. He figured out electrons and atoms couldn't just have any old energy.
Only specific amounts.
Only specific levels, like steps on a ladder. They could only jump between these steps.
The quantum leaps?
Those are the quantum leaps. And they jump by absorbing or spitting out a photon, one of those light quanta. His institute in Copenhagen became this hub.
For brilliant minds.
Yeah, all these young geniuses working together to build a proper theory.
And by 1925, they had the equations. A whole new physics?
They did. It replaced Newton's mechanics for the small stuff, and it was a huge success. Suddenly, things made sense.
Like what?
Like, the periodic table of elements. Why are there those specific elements? Why is the table structured that way?
Quantum mechanics explains that.
It explains it perfectly. The structure of the table, why elements behave the way they do. It all comes from solving the main equation of quantum mechanics. Basically, all of chemistry boils down to this one equation.
That's staggering. One equation for all of chemistry.
Pretty much. But then it got even stranger thanks to Werner Heisenberg.
What did he add to the weirdness?
Heisenberg had this dizzying idea. He said particles like electrons don't necessarily exist in a definite place all the time.
Come again. They don't exist.
Not in the way we usually think. It's more like they only pop into reality, into a specific location when we measure them or interact with them.
So between measurements.
Between interactions, an electron is more like a cloud of possibilities, a blur. You can calculate the probability of finding it somewhere if you look, but you can't say for sure where it is when you're not looking.
Okay, that's really hard to grasp.
Yeah.
Reality is only sharp when observed.
Kind of. Think of watching a ceiling fan. You don't see the individual blades when it's spinning fast, just a blur, right?
Yeah.
An electron is a bit like that, but more fundamental. It is the blur of possibilities until an interaction forces it to choose a state.
And the quantum leaps are random.
Probabilistic. You can't predict exactly where an electron will jump to, only the odds, which is a massive shift. Physics used to be all about exact prediction.
Einstein hated that randomness part, didn't he? The God does not play dice line.
He famously did, which is funny because he nominated Heisenberg for the Nobel Prize for this very work. He saw its importance, but it deeply bothered him.
And that led to big debates. Einstein versus Bohr and his group.
Oh yeah, years of debate. Einstein kept coming up with clever thought experiments like his box of light, trying to poke holes in quantum theory, show it was incomplete or inconsistent.
And Bohr.
Bohr always found an answer. He'd analyze Einstein's experiment and show how quantum mechanics still held up. It was this amazing intellectual sparring match through letters, talks.
Did they ever agree?
Not completely. Einstein eventually accepted the theory was logically sound, but he always felt there had to be a deeper deterministic reality underneath. Bohr argued that no, reality at that level is fundamentally about interaction and probability. Observation isn't passive, it helps create the reality we see.
And a century later, we're still arguing about what it all means, even though we use it constantly.
Pretty much. Quantum mechanics works incredibly well. It's the basis for so much technology. But what it tells us about the nature of reality, that's still up for grabs.
It described how things interact, but maybe not what they are.
That's one way to look at it. Is reality just interactions? Are we missing something? Or do we just need a whole new way to think about what reality even is at that scale?
So it's like a perfect recipe that works every time, but we don't fully get why the ingredients combine like that.
That's a fantastic analogy. It's this incredible, powerful tool, this dive into reality's depths. But maybe it's flawed or incomplete or just a clue to something even deeper we haven't grasped yet.
And the debates continue.
They do. That image of Bohr's blackboard, still with Einstein's thought experiment sketched on it after Bohr died, it says it all, doesn't it? The quest continues.
Okay, lesson 3. The architecture of the cosmos. We're zooming out again, right?
Yeah.
Big picture time.
Way out. Looking at the universe on the grandest scale. And this builds on both relativity and quantum ideas. The text makes a nice point about visions in science.
How imagining things differently comes first.
Yeah, before the math and experiments sometimes. Just seeing a new possibility.
And our vision of the cosmos has changed dramatically over time. Started simple, Earth flat, sky up.
The default view for ages. Then, Anaximander, an ancient Greek thinker, had this radical thought. Maybe Earth is just hanging there in space with the sky all around.
Huge leap. And then the Greeks figured out Earth was a sphere.
Aristotle and others made strong arguments for a spherical Earth, yeah. And that model, Earth at the center of a spherical cosmos, lasted for centuries.
Until Copernicus.
Until Copernicus said, hang on, maybe the sun is at the center and Earth is just another planet going around it.
Demoted. From center stage to just one of the chorus lines. That must have been tough to swallow.
A massive shift in perspective, and it didn't stop there. We realized our sun is just one star.
Among billions.
Right.
In our galaxy, the Milky Way.
Right. And then in the 1920s and 30s, Edwin Hubble and others showed our galaxy is just one.
Among billions of galaxies.
Billions and billions, stretching out as far as we can see. That Hubble telescope image the source mentions, just mind-boggling. Galaxies everywhere, each with billions of suns, probably trillions of planets. The scale is just
unimaginable, really. And this whole vast structure isn't static either because of general relativity.
Exactly. Space isn't just an empty stage. It's dynamic. It curves, it stretches, it ripples with gravitational waves. It can collapse into black holes.
So putting it all together, what's the current picture?
The current picture is the Big Bang. About roughly 15 billion years ago, the entire observable universe was compressed into an incredibly hot, dense state. Smaller than an atom, and then it started expanding.
And it's been expanding ever since.
Yep. Cooling down, forming stars, galaxies, planets.
Which naturally leads to the question, what about before the Big Bang?
The million-dollar question. Or maybe billion-dollar.
Yeah, are there other universes?
Those are the frontiers. The honest answer, we don't know. We have ideas, theories, but no solid evidence yet.
Okay. So from the cosmic architecture down to lesson 4, particles. The smallest building blocks.
Right back down to the microworld. What is all that cosmic stuff made of? We know about atoms, Nucleus with protons and neutrons, electrons whizzing around.
But even protons and neutrons aren't fundamental.
Turns out, no. In the 60s, Murray Gell-Mann figured out protons and neutrons are made of even smaller things. He called them quarks.
Quarks. Funny name.
Yeah, he borrowed it from James Joyce. So, fundamentally, almost everything you touch, everything you are, is made of just two types of particles: electrons and quarks.
That's it. Electrons and quarks.
Pretty much the basic matter particles. Now, what holds the quarks together inside protons and neutrons? That's another particle.
Cool.
Gluons. They're the glue.
Okay, electrons, quarks, gluons. Any others we need to know about?
A few key ones. Photons, the light particles. Neutrinos, tiny, almost massless things that barely interact. And the Higgs boson, the one they found recently, which is related to why particles have mass.
So maybe fewer than 10 basic types in total.
Something like that. It's amazing, really. The whole universe, all its complexity, built from this tiny Lego set of elementary particles.
And quantum mechanics describes how these Lego bricks behave.
It does. But remember, they're not really like little solid bricks. They're quanta of fields.
Fields, like force fields.
Sort of. Imagine underlying fields filling all of space. The electromagnetic field, for instance. A photon is a little ripple, a quantum excitation in that field. Electrons and quarks are excitations in their own fields.
So particles are like vibrations in these invisible fields.
That's a good way to think of it. Tiny wavelets constantly popping up, interacting, disappearing, according to quantum rules.
And even empty space isn't really empty. It's full of these fields fizzing.
Exactly. Even in a vacuum, there's this constant low-level activity, tiny quantum fluctuations, particles briefly popping into existence and vanishing again. It's a far cry from Newton's cold, empty void.
This whole picture, this particle zoo and their rules, that's the standard model.
Yes. Developed mostly mid-20th century, finalized in the 70s. It describes all the known elementary particles and their interactions except gravity. And it's been incredibly successful experimentally. Finding the Higgs was a huge confirmation.
But physicists aren't totally happy with it. The text hinted at that.
Well, it works, but it's not. Elegant, maybe? It feels a bit stitched together, lots of different particles, forces, seemingly arbitrary numbers you just have to plug in. And some of the math needed to get predictions. It involves techniques that feel a bit like mathematical tricks to get rid of infinite values.
Sounds messy.
It feels messy to some. Even Dirac, one of the founders of quantum theory, felt it wasn't the final answer. Plus,
There's dark matter.
there's dark matter, this mysterious stuff that has gravity but doesn't interact with light. Makes up most of the matter in the universe, apparently. And it's not in the standard model. It's made of something else entirely.
So the standard model is like the best map we have, but it's missing a whole continent.
That's a great way to put it. It's our best description of the normal matter, the stuff we're made of, but it's definitely incomplete.
Have there been attempts to make a better, more elegant theory?
Oh, many. Theories trying to unify the forces or predict the particle properties. But so far, the experiments haven't backed them up. That's how science works, though. You try ideas, you test them, most don't pan out.
So for now, we stick with the standard model, warts and all.
It's the reigning champ, despite its quirks. Maybe, as the source suggests, we just haven't found the right angle yet, the perspective that reveals its hidden simplicity.
It's still amazing, though. A handful of particles flickering in and out of existence, making up everything from galaxies to us.
It is pretty poetic when you think about it that way.
Which leads nicely into Lesson 5, Grains of Space. This sounds like where we try to bridge the gap between the big relativity and the small quantum mechanics.
Exactly. We've got these two pillars of 20th century physics, general relativity for gravity and the cosmos, quantum mechanics for particles and forces, both incredibly successful, both led to huge advancements.
But they don't play nice together.
They fundamentally clash. One describes a smooth, curvy space-time. The other describes a lumpy, probabilistic quantum world. You can't just, glue them together. They contradict each other at a basic level.
Like trying to use two different maps of the same place that show completely different features.
That's a good analogy. They work brilliantly in their own domains, but where they overlap, like trying to describe gravity at very small scales, or the inside of a black hole, or the Big Bang itself, they break down.
So quantum gravity is the search for the unified map.
That's the holy grail, a theory that combines quantum mechanics and general relativity into a single, consistent description of reality. It's arguably the biggest challenge in fundamental physics today.
And finding a solution could be a massive breakthrough, like previous unifications in physics.
Historically, yes. When conflicting but successful theories meet, it's often where the next big revolution happens. Newton uniting celestial and terrestrial mechanics, Maxwell uniting electricity and magnetism, Einstein himself. So this clash is seen as a huge opportunity.
And loop quantum gravity is one of the main contenders trying to do this.
It's one of the leading approaches, yes. It tries to take both general relativity and quantum mechanics seriously and weave their principles together.
And what does it suggest? What's the core idea?
Well, it leads to some pretty mind-bending consequences. The basic logic goes something like this. General relativity says space is dynamic, it can bend and warp.
Okay.
Quantum mechanics says physical fields are made of quanta, discrete packets.
Right.
So if space is a physical field, the gravitational field, then space itself must be made of quanta.
Whoa, space is grainy, made of little bits.
That's the prediction. Not smooth and continuous, but fundamentally pixelated, made of atoms of space.
Atoms of space.
Yeah.
How small are these pixels?
Unimaginably small. The Planck length, small. Billions of times smaller than an atom's nucleus. You'd never notice the graininess in everyday life.
And the theory describes these
Yeah.
loops or rings.
Yeah, the mathematics describes these fundamental quanta of space, sometimes visualized as loops or nodes in a network. These interconnected loops create the fabric of space.
So they're not in space, they are space.
Exactly. Space emerges from their relationships, their connections. It's not a pre-existing container.
That's radical. What about time? Did I get quantized too?
Even more radical things happen with time. In loop quantum gravity, the smooth, continuous flow of time, it disappears at the fundamental level.
Time disappears, so everything stops.
No, things still happen, processes still occur, but they don't happen against a background clock ticking universally. The equations describing these quantum grains don't have a test variable for time in the usual sense.
How does change happen then?
Change is relational. Processes evolve relative to each other. Time isn't this absolute river. It emerges from the relationships between events at this fundamental quantum level. Our sense of a smooth flow of time is, again, a large-scale approximation.
So the deep reality is just interacting quanta of space and matter, no stage, no clock. And our world is like a blurred view of that.
That's the picture loop quantum gravity paints. Like seeing a smooth lake surface, but knowing it's really zillions of frantic water molecules. Of course, the big challenge is
Testing it, finding evidence.
exactly. How do you probe things at the Planck scale? One place theorists look is extreme environments, like black holes.
How does loop quantum gravity change black holes?
Well, if space is grainy, matter can't collapse to an infinitely dense point of singularity because there are no infinitely small points. There's a minimum size.
The collapse stops.
The idea is that quantum pressure resists the crush of gravity at that tiny scale, forming an incredibly dense object, maybe called a Planck star?
A Planck star.
Hypothetical, but maybe the size of an atom containing the mass of a collapsed star. And these might not be stable forever. They could eventually bounce.
A black hole could bounce.
Explode. That's a prediction. It might look like a very slow process from the outside because time gets so warped near a black hole, but fundamentally it could rebound. Some scientists are looking for signs of ancient, tiny black holes exploding today that could be a signature of quantum gravity.
And what about the Big Bang? Does it become a big bounce too?
That's another fascinating possibility explored in loop theory. Maybe the Big Bang wasn't the absolute beginning, but a rebound from a previous collapsing universe. A universe that passed through a state where space and time, as we know them, didn't exist.
So no beginning, just cycles.
It opens up that possibility. It shows how physics keeps pushing us beyond our intuition, revealing layers of reality we never suspected. Loop quantum gravity is one attempt to decode those clues.
Okay, that's a lot to chew on. Lesson 6. Probability, time, and the heat of black holes.
Yeah,
Sounds like we're connecting more dots.
we're bringing in another major area of physics, thermodynamics, the science of heat. It started with a simple question. What is heat?
And the old idea was some kind of fluid? Caloric.
Yeah, that was the early guess. But Maxwell, Boltzmann, and others figured it out. Heat is about the motion of atoms. Hotter stuff just means its atoms are jiggling around faster, more randomly.
Makes sense. But the source asks a deeper question. Why does heat always flow one way? Hot to cold.
Ah, yes, the arrow of time connection. Why does a hot coffee cup cool down, but a cold one never spontaneously heats up by sucking heat from the air?
It seems obvious, but why?
It's fundamental to our experience of past and future. Processes without heat, like planets orbiting, ideally, look the same forwards or backwards in time. Add heat, add friction, and suddenly there's a direction. Past is different from future.
Because heat only flows one way.
Because heat flowing hot to cold is the defining feature of that difference. And Boltzmann's amazing and initially controversial answer was, it's just probability.
Probability again, like in quantum mechanics.
Related, but different. Boltzmann said it's not a strict law that heat must flow hot to cold. It's just overwhelmingly, astronomically more likely.
How does that work?
Think of all the atoms in the hot coffee and the cooler air. There are countless ways they can bounce off each other. The vast majority of those random collisions will result in the faster coffee atoms giving some energy to the slower air atoms, evening things out.
So it could go the other way. The air atoms could all just happen to hit the coffee atoms just right to make the coffee hotter.
It's not physically impossible, just ridiculously improbable. Like, you'd wait trillions of times the age of the universe to see it happen for even a small cup. The odds are stacked massively in favor of heat spreading out.
And this was hard for people to accept at first, that a fundamental process was just about chance.
Very hard. Boltzmann faced a lot of opposition. Tragically, he didn't live to see his ideas fully vindicated. But this statistical understanding of heat is now central to physics.
So this isn't the weird quantum probability, but probability based on not knowing all the details.
Exactly. It's statistical mechanics. We don't know exactly what every single atom is doing. There are far too many. But we can make incredibly accurate predictions about the average behavior, the macroscopic properties like temperature and pressure, using statistics.
So the reason the spoon heats up is because that's the most probable outcome given all the random jiggling.
Precisely. It's about the collective behavior that emerges from the chaos. Now, extending these ideas of heat and statistics beyond simple gases or fluids, that's been a huge part of physics. But applying it to gravity, that's been tough.
What does hot gravity even mean?
Well, we know what a hot electromagnetic field is. It's vibrating radiation, like the light and heat in an oven made of photons. But the gravitational field is space-time. So a hot gravitational field would mean vibrating space-time.
Vibrating time, what would that be like?
We don't really have the equations yet, not from a fully accepted theory of quantum gravity. This brings us right back to the deep puzzle of time. What is its flow?
It seems like such a basic part of reality, but physics struggles with it.
It does. Our formulas describe change over time, but time itself seems unique. It flows. The present feels special. But why? Special relativity already showed the present isn't universal, it's relative.
Einstein said the distinction between past, present, future is an illusion.
A stubbornly persistent illusion, yeah. So, if the flow isn't fundamental, where does our powerful feeling of it come from?
And the suggestion is it's linked to heat.
It seems to be. The clear distinction between past and future only appears when heat is flowing, when entropy, disorder, is increasing. And heat is linked to probability, which is linked to our incomplete knowledge of the microscopic details.
So the flow of time we experience might be a statistical effect, emerging from the fuzziness of our view.
That's a leading idea. Time's error emerges from thermodynamics and statistics, not from the fundamental reversible laws governing individual particles. Our consciousness, our memories, they rely on these irreversible statistical processes.
So a being who could see every particle perfectly might not experience time passing at all.
Perhaps not. The universe might look like a static four-dimensional block to them. It's our blurred macroscopic perspective that creates a sense of flow. It's complex, we're still figuring it out. Time is right at the intersection of gravity, quantum mechanics, and thermodynamics.
A major puzzle. But there was a clue. Stephen Hawking and black holes.
A massive clue. Hawking showed, by combining quantum ideas with relativity near a black hole's edge, that black holes aren't perfectly black. They should glow very faintly. They radiate heat.
Oh, holes are hot.
They have a temperature. It's incredibly low for big black holes, but it's real. It's called Hawking radiation. This was the first concrete result that truly linked quantum mechanics, gravity, black holes, and thermodynamics. Heat.
So black hole heat is like key.
It's seen as a kind of Rosetta Stone, yeah.
Yeah.
It speaks all three languages, quantum, gravity, thermal. If we can fully understand why black holes are hot, it might tell us profound things about the nature of space, time, and quantum gravity.
Wow. Okay, deep breath. Final lesson. Ourselves.
Yeah.
After all this, where do we fit in?
The ultimate question, maybe. In this universe of shifting quantum fields, expanding space, probabilistic laws, what does it mean to be human? What about our consciousness, our values, our sense of self?
And the text admits we don't have easy answers. We understand ourselves least of all, in some way.
True, but we are part of this universe. We're not just spectators looking in from outside. We're made of the same quarks and electrons. We're subject to the same laws. We're nodes in the network, observing, thinking, sharing. Our view is inherently from within.
And our understanding of our place has certainly shrunk over the centuries. From the center of everything.
To a speck of dust on a speck of dust in a possibly infinite cosmos. It's humbling. Like an only child realizing the world isn't all about them.
So science doesn't really support the idea that humans are the pinnacle of creation.
From a cosmic perspective, it's hard to argue we're objectively special. We're a result of these processes, one complex pattern among countless others, living on a small planet in a fairly ordinary galaxy.
And our perception is filtered through our senses, our brains.
Absolutely. We don't see raw reality. We construct a model based on limited sensory input, interpreted by a brain shaped by evolution. Our concepts, our understanding, they're not fixed. They evolve as we learn more.
But we are learning. We're getting closer to understanding the world we're part of.
I think so.
Yeah.
Slowly, imperfectly, sure. Science is this ongoing process, like the source says, like tracking an animal, carefully observing, making inferences, testing hypotheses, being ready to be wrong, but trusting we can get better at it.
It's about building knowledge that reflects reality well enough to be useful.
Right. Knowledge that helps us navigate the world. And fundamentally, the stuff we're made of, the stuff doing the thinking and observing, is the same stuff as the stars and the nebulae. We're not separate.
We are quite literally stardust trying to understand the stars.
Beautifully put. So the deep dive ends here, leaving you perhaps to think about your own nature, your own place within this incredibly vast, strange, and wonderful reality that physics continues to unveil.